Imagine that you were given the choice between earning $100,000 a day for a month, or you were given the choice to earn $1 on the first of the month and then $2 on the second of the month, but then $4 on the third of the month and $8 on the fourth of the month. Which of the two options should you choose? The answer might surprise you. It's actually one of the oldest kind of examples of critical growth that has happened since the invention of algebra. And it's one that's stumped mathematicians. It's inspired ideas about growth and interest rate and how it is that we expand across the planet into the universe, how it is that bacterial cultures form, how it is that we use up fossil fuels. The number of applications are just enormous. And of course, there's a pretty big one in how to make money. So the first question I give you is just a little bit of a riddle, and it's a riddle that comes out of India because, as we know, India and the Middle East were the birthplaces of algebra, right? And even within the word algebra, you can hear that it has Middle Eastern roots. So this question was actually posed not so long after the invention of chess. And as it turns out, chess took the country of India by storm. It was a favorite amongst the royalty there. And so this little riddle came up where essentially the story was that the king was such a fan of playing chess that he invited anybody in his kingdom to come and challenge him, and to kind of keep the interest high. The king offered whatever prize or wager the challenger wanted. And as it happens, there was a chess master who decided to accept the king's offer, and he asked solely for the reward, should he win, that it would be the amount of rice equivalent to putting 1 grain of rice on the first square of the board, and then 2 grains of rice on the second square of the board, and then 4 on the third, etc., etc. And the king laughed at this, thinking that this was an absurdly small wager, but accepted the challenge, lost, and graciously, because he was an honorable king, in truth, a king who valued truth, went and got a bag of rice and began counting out the individual grains of rice. And so this is an interesting one. Let's see how it relates. We'll go back to our money example and connect these two different stories and see how it is that we could actually use this to maybe deceive people into what appears to be a very small amount of rice or money. So let's start off with the one for the dollar. So how can we express what's actually happening here? Let's use our mathematics to extend our common sense. So we're getting $1 a day for the first day. So let's talk about that. We'll go ahead and call this, I don't know, maybe our input will be D, the number of days, and then the amount of money we get at the end of all of this will maybe be, I don't know, maybe amount. We'll put amount right there. And so we're looking to say, okay, I am receiving $1 on the first day. So on the first day, we get $1. That gives us $1. I'll put my work in the middle here. This will be our work. Okay, what about on the second day? On the second day, there is 1 plus 2, right? Which would be 3. Okay, not too bad. On the third day, there would be 1 plus 2 plus 4. And so that would be, 7 grains of rice? Like, this is not even enough for one meal. On the fourth day, you've now got 1 plus 2 plus 4 plus 8, and that would be 1 plus 2 is 3, plus 4 is 7, plus 8 is 15. So by almost the first week, you still don't have enough to even fill a bowl, which seems like quite the small wager, but we can be a little bit broad here and notice that what's happening, if we wanted to talk about just this last term here, is that this last term is going to be easiest thought of, or most easily thought of as just repeated multiplication. After all, for our fifth day, this would be 1 plus 2, and then the next one would be plus 2 times 2, and then the next one would be 2 times 2 times 2. Oh, but maybe we get tired of writing it that way. We'll just call this 2 to the third power, and then we'll put it as 2 to the fourth power for the last one. Okay, and so then we could calculate all of this up. In fact, what would that be? That'd just be adding 16 to the one above that, so 31 total grains of rice. It doesn't seem like taking this pattern is really going to do us much good. But let's maybe extrapolate. Let's play around with what this last term is going to be. Like, let's grab, if we can, this 2 power, and notice that all we're doing on any given day is just adding up another multiple of that 2. So maybe we'll put this pattern on hold for a moment, and we'll just consider what is happening with that last term, that 2 to the x, where x is just constantly going up by 1 step. Let's use our graph to explore this one. So we've got 2 to the x. What's happening with that one? Well, when we talk about, let's see, when we get all the way to, maybe we'll put in 5 here. We'll just step this up so we can expand our common sense. So we got 2 to the 5th power. Well, that would be 2 times 2 times 2 times 2 times 2. Okay, that's a lot of numbers to think about. What do we have there? Let's pull out our calculator. And we can actually use on most calculators, there's going to be a button that looks like it's got an exponent, either with a little caret so you can put it in, or it's got this kind of symbol where it says x to a y. So I'm going to use this button where it's 2 and then x to the y, so that says 2 to the, you can see a caret appeared up here. So I've got 2 to the 5th. Let's go ahead and plug that in. That says 32. Okay, so we can go ahead and put in 32, and I'm going to try to keep this pretty small. I'm going to maybe make this where it's 50 and 100. So 32 is going to be something that's quite small, no problem. And then the next part, let's go ahead and consider what's going to happen if I do 2 to the 10th. I'm going to try to jump this up a little bit, 2 to the 10th. And we get 1024, so that's actually quite a big jump. So we went from 5 to 10, and then I need to make sure that I've got to 1024. How did that happen? I'm already off of my screen. Right? This would be 200, and if I went up even more, that'd be 300, 400, 500, 600, 700. I'm already off of my screen. Okay, that's quite surprising. Maybe I made my scale too small. Let's try making this something where I'm going up by 500. So now I've got 500, and then I'll make this 1,000, and I'll make this one, let's see, the next one would be 1,500, and then the next one would be 2,000. And I'll see if this is going to be enough, because then I would have 3,000 up here, and we'll see if I have enough to actually begin putting in all of my data. Okay, so we said that 5 was going to be 32, so I actually need to bring that down quite a bit. That's going to be just down here. And then the next value is going to be 1024, so that at the 10 was 1024. That's going to be just barely right there. And then let's do 2 to the 20th. So we'll do 2 to the 20th. Up to the 20th. That'll be 1,048,000. I still don't have enough room here. This is just absolutely exploding. I mean, after all, we started off when my very first step was just 1, so I went from here to here, and then I went to 3. That was barely more than 1. Like, it looks like I was doing absolutely nothing, and then all of a sudden, it just exploded. I can't even get this next one on my graph. I would have to step this thing down to the millions, and we start to see why this was such a clever wager, because if you go up to a traditional chessboard, there was 1, 2, 3, 4, 5, 6, 7. There's 8 by 8 squares. That's 64 squares, which means that eventually you were going to get to 2 to the 64th that you were adding, and let alone what the pile was that you were adding on top of 2 to the 64th is already a huge number. In fact, let's actually try to calculate it. Let's see if I can even put this into my calculator. 2 to the 64th. And there you have it. Let's see what that is. That's over this is the millions. This is the billions. This is the trillions. So you've got a billion trillions. You have 18 billion trillions of grains of rice that you are working with here. To put this into perspective, this is more than the global production rate of the world. And that's how much you would have had if you just simply got to that last little square by doubling up from 1 grain of rice. And so as it turns out, this was quite the logic riddle, quite the folk's tale, because it warned of these kinds of patterns. Because as it turns out, the king could not have possibly fulfilled this bet. It would have broken him. It would not have only broken him, it would have been enough to cripple the world economy that we have currently. So this is what we call exponential growth. And exponential growth has been called by Einstein to be the most powerful force in the universe. This idea of saying that something is doubling and then doubling again and doubling again is how we get some very fantastic claims. In fact, here's a very interesting one. Suppose you take a piece of paper, we'll use one that I have right here lying around, and imagine I was going to fold it in half. Okay, in fact, let's just do it. So I take a piece of paper and I fold it in half, and as we can see, it's now twice as thick. Right? Especially if I kind of push it down. You can even push it down a little bit. But we could always fold this again. So maybe I could fold it again. And so now it is 4 times as thick, right? But still quite small. In fact, let's do it maybe a few more times, and eventually I'm going to not be strong enough to do this. It's already getting a little bit difficult. Okay, so now it's 8 times as thick. Okay, but still not all that thick. What if I was to do it one more time? That'd be 16 times as thick. And again, it's barely as big as a coaster. So here's my question for you. How many times would I need to fold this piece of paper for it to be able to, I don't know, let's say, be as tall as the distance between me and the moon? And I'll give you just a moment to think on that one. So pause the video here and just throw out a number. See what you can guess. How many times do I have to fold this thing so that I am not just able to be as tall as me, as tall as a building? I want to know, how long does it take? How many folds does it take so I can reach to the moon? Well, as it turns out, if you begin folding this around, and it's a pretty simple calculation to do, after about 7 folds, this gets to be about the thickness of a notebook. So we can use one that I've got lying around. Maybe about a notebook's thick. But then if you get to 23 folds, you actually have this entire thing has become as big as a kilometer. So what's more interesting than that is maybe after 30 folds, you will actually get something that is all the way out into space. We've exceeded the Earth's atmosphere. And by the time you get to 42 folds, you will actually have gotten between here and the moon. So now to help capture this, I have an interesting question for us. Suppose that at every minute you have a bacterium, right? And every minute is going to be doubling. Which would make sense. It's going to be splitting, it's going to be forming of itself, it's going to be duplicating. And we'll say, okay, we're starting at time 0, I have 1 bacterium. At time 2, or when I have 1 minute passed, when I have 1 minute have passed, then there will have been 2. So we can actually start to write this out using our notation. So we can say at time equals 0, this was going to be something that had, let's see, 1 bacterium. So what we want to call it, the amount, we'll call it the amount. Okay, so that'd be A, would be 1 bacterium. At time equals 1 minute, so there's been 1 minute of this experiment, the amount would be 2 bacterium, something that you would not even be able to see with the naked eye. So now the question I have is, let's say that you leave for an hour and you come back and you find that the test tube is 1/8 full. Okay, so we can actually sketch that out. Let's imagine that we have a test tube, and inside of it we have it being 1/8 full. So here is 7/8, here is 1/8, and this is how much we have filled up with the bacterium. How long do you have before this bacterium culture explodes out of the test tube? And I'll give you again, just kind of think on that for a moment. At this point, it's been almost an entire full day for it to reach this 1/8. Do we think we maybe have, 7 days left? Well, not if we account for exponential growth, because exponential growth says that we aren't going at a way that is consistent with what we had before. We're going at a way that continues to expand from what we had before. So in truth, if you're looking at this as being 1/8 of the amount that you have, then you have to imagine that the next moment it's going to be doubling. So all of a sudden it's going to go into 1/4 of it will be full. There'll be 1/4 this entire thing filled up with our bacterium cultures. What about the next minute? The next minute you're at 1/2. So now 1/2 of your test tube is at bacterium cultures. How much longer do you have until this thing explodes? Well, you only have 1 more minute. At 1 more minute, this entire thing has gone from 1/2 to double of 1/2. So now the entire thing is full. So if you come in and you see that you have this bacterium culture and it's at 1/8, and this was, when you first come in the morning, we'll call this time equals 0. You have 1, 2, 3 minutes until this entire thing is about to explode. Kind of crazy. But again, this might feel like a little bit of just I don't know, maybe a math puzzle, something for math class. But now take a moment. Where have you heard exponential growth before? Perhaps you've heard it mentioned all across the news, like that we have an exponential growth or an exponential increase in the amount of fossil fuels that we use. Or perhaps that there's an exponential growth in populations, human populations. Perhaps you hear something like, I don't know, here's a couple things that I just pulled off of the internet, right? Exponential growth of computing. So the computing power that we can now do today, right? If you look over here, has just been absolutely astronomical, right? If you look over here at the human population chart, again, this is something that has just increased crazily, because if you have a family and every family continues to, I don't know, perhaps have 2 children, 3 children, right? Anything more than 2 children is going to all of a sudden cause this entire thing to expand. And when it does, it expands more and more and more. You begin to notice that this is a situation that becomes very unmanageable very quickly. So the interesting way that I like to think about this one is maybe not in how much time do you have as the observer, but let's now put us in a different perspective. At what moment would you have started to realize, if you were a bacteria, that you were running out of space? Would it have been over here at this minute when you had plenty of, when you had 7/8 of the test tube still full? What about over here when you still had 3/4 of the test tube full? At the 1/2 mark, might you have started to recognize that, like, hey, it's getting a little bit crowded. Perhaps we want to maybe start shopping around for a new test tube. What about right before? What if we say that at the 90% mark, when we only have 10% of our room left to expand, is when we start to feel uncomfortable? Where is that in this entire diagram? Well, we can actually calculate that, and we'll do that in the next class, because we'll be looking for, at what moment do we start to say that this entire thing is 90%? We can already see that it's going to be something that's between 2 and 3 minutes. So that means that the time that you start to feel uncomfortable as a bacterium, you've got less than 1 minute to go and find a new test tube. Otherwise, you're about to overflow. And that's a lot of the situation that we see our world in today, when we have populations expanding, monetary growths, when we have computing powers, when we have uses of fossil fuels. This is why it's such an important thing. Not to mention a lot of medical situations like epidemics and pandemics, when we start to recognize that a small amount of give in the beginning can become very unmanageable very quickly. So I told you this exact same principle happens in money a lot of times, and I want to show you how it does with this example. This is actually one of the first examples that was studied for the way that banks could behave, how often they could give out interest, and it was studied by a mathematician named Bernoulli. And so here's the general idea. The general question is, let's suppose that you had a bank account. The bank account promises to double the amount of money you give them at the end of every year. This is a very generous bank account. So now let's think about what's going to happen. I put in $100. So for an example, we've got maybe our table here. We'll organize our money into this table. So we'll say that on the first year, at year 0, I put in, let's say, $100. At the end of that year, when 1 year has gone by, you will have $200. This is a very generous bank. Okay. Now, the question is, what will happen if instead of putting my money in this bank, I find out that there is a second bank, and the second bank promises to double my money, but they suppose they're going to do things a little bit differently. They promise that they are going to double half of my money twice a year. Okay, it sounds like it should be an even trade-off. I mean, after all, so this is bank 1. Bank 1 says it's going to go this way. And then we look at the next situation. The next one says, okay, well, I'm going to double it twice a year. So maybe in this next situation, I can't do it where I'm just stepping up by 1 year each time. Now I'm going to be stepping up by half a year. So let's take a look at what that would be. Okay, in the beginning, I'm going to put in the exact same amount of money. Okay. A half of a year comes by, and they say they're going to double half of my money. Okay, so doubling half of my money would be doubling $50. So that would be now what? I have my original 100 that I have in here, and then I've gained $50 more. Okay, so that seems so far so good, right on track. But then we get to this 1 year mark, and then we are going to double my balance, the other half of my balance. But now we get at the end of the year, and again, they promise to double half of my balance. So now what it is that I have is I have $150 from the last time that they doubled it. If they double half of my balance, that would be doubling $75. Okay, so now it would be 150 where they've doubled 75 of those dollars. So I get that again. That would be $225. So notice the difference. If I do this doubling of half, I'm actually coming out 25 bucks ahead. This seems like a really good reason for me to switch banks. But can be where looking at the structure of this is much more important than looking at the answer to the question, because now is when we can start to expand this into something much more powerful. So let's take, for example, let's scooch this on over, shall we? Let's bring this whole thing over here and now start to examine the structure, this kind of ripple effect that we're seeing. If we look at this second one here, all this was saying that I was going to have $100 plus $100. So I had $100 plus $100. But in this situation over here, you had $100 plus half of $100. So you had $100 plus one half of $100. And then from there, you were saying, okay, there's kind of this ripple effect, right? Where now I have one half of $100 plus $100, and then I've got again plus one half of this result right here. But notice in every single time, the $100 was was repeating itself. After all, we could talk about this with any amount of money. Like we could have looked here and said that this was really just $100 and captured just the idea of the doubling, where I have 1 plus 1 instance plus 1 instance of this $100. And it starts to make this second part up here, the second situation, even clearer if we do it. So now let's look at it again, where I have 100, but I have 1 instance and a half an instance of that, okay? Because now, if we look at this under the exact same light, notice what we have. We have, again, 100 times 1 and a half instance that I'm about to multiply again by saying that I want to have that instance from before and another half instance. Oh, let's put a plus sign there. So now we start to get this idea of kind of the grouping, and the grouping we found the repeat, right? So we have $100 that I'm about to keep the same and grow by half. Then I take that amount and I keep it the same and I grow it by half. So that would be the next kind of layer in our multiplication. Keep this all the same and grow it by a half. And now we start to see what happens if we do this over and over again. Because, for example, what happens if we have another bank that does it every 4 months? This would be 3 times a year. Well, now we've got a way to really expand this out. So now we're talking about saying that we have $100 and we're just looking at it in terms of its instances. So now I have 1 instance of it and however many times. So if I'm doing it every 3rd of a year, then I'm going to be increasing my amount by a 1/3, but I'm going to be doing that 3 times. After all, up here, didn't we have it where it was 2 times? So I was increasing it by a half and I had it 2 times. Here I increased it by 1, but I only had 1 of those sets of parentheses. What if I was doing it where it was every month? Well, that would be 100 that I'm starting with, and I'm always going to be at least keeping it the same, but then I'm also going to be growing it by an amount. So if it's every month that I'm doing this pattern, then I'm going to be growing it by 1/12, but I'll be doing this 12 times. And so the curious thing is what happens when you start looking at all of these numbers. And I've got a table here. Take a look at what happens, because you may think that as we keep doing this, we keep getting more and more money. And so this might be a nice little con that we could go run on the banks and convince them that they should be doing the exact same thing as advertised, just possibly more frequently. But as it turns out, we actually get into a bit of a cap. I mean, after all, we can start to see that really this part right here, which in the table is structured as 1 plus 1 over n all to the nth power. We can see that over here that we have the 3 in the denominator of the fraction and also to the exponent, that this actually begins to plateau. It doesn't go on forever. And we can see that because if we start looking at larger and larger frequencies of doing this, the twos, the single places begins to lock in, the next place begins to lock in. You can start to see that it kind of settles on being a 7 after a while. And then if you keep going down the line, the next place kind of locks in as you get bigger and bigger numbers. The next place locks in as you get bigger and bigger numbers. And we actually begin to approach a number all the way through that becomes 2.71828, etc. And this becomes literally the upper bound for this kind of scam that we could run. And so do you continuously make more money the more often you do this? Yes, but eventually you're having to jump up in a huge magnitude of frequencies for it to budge even a small little bit. So that's why we like to refer to this as an upper bound. And in fact, this is the upper bound that appears in all of these growth situations. So we can actually use this to help make our calculations much more easy. This is what is referred to as the constant E. And it's given a bunch of different names. Euler's number, because the mathematician whose last name was Euler was one of the first people to really anchor down this and calculate it very accurately, so it's named after him. But this acts as what we would say is our upper bound for how much money we could make if we are having our continuous compound interest. So, for example here, if you were to double the money that you were putting in, how would it affect the final amount? Well, we could look at this as saying that really what we're doing is instead of our 100 in the front, we would put that in as saying now we would have 200 times 1 plus 1/12 to the 12th. That would be the situation if I was compounding it every month. So if that's the case, then we can almost imagine like I was doing the exact same thing as here, but I was doing it in 12 different bank accounts. I had 12 groups of the 100. And if you don't see that, we can just separate that really easily. Oh, sorry, two groups of the 100. We can see that as saying it's like I have two of these situations right here. So what happens if we double the money we put in? We get double the money that we have coming out. And it would be captured underneath this same upper bound, where the upper bound is going to be 200 times, well, this entire thing is eventually going to cap out at E. So I've got 200E as being the maximum boundary for this entire situation. Okay, so what happens if we double the amount of money we're putting in? We're going to double the return in either situation. Okay, if you invest 2 years or 3 years instead of just 1, what happens? Okay, well, let's play around with that one. So now again, we're going to use this 100 times everything as an example. If I was going to do this entire thing for 2 years, then that would be 1 plus 1/12. And then instead of it compounding 12 times, it would compound 24 times, right? This up here was our time. We can call that T. It was the amount of time that I was letting this thing kind of run for, right? And then every single time, how much was I getting? I was getting 1/12. So if I ran this entire thing for 2 years, then that would be like running it for 24 months, where every month I get 1/12 of that interest rate, of that yearly interest rate. So how does this affect our total amount? Well, it's actually going to scale this up quite a bit, because we can view this entire thing as 100 times 1 plus 1/12 to the 12th squared. And we can use our exponent rules to recognize that what's really happening is now I've started to look at this thing as growing even more powerfully. So the second year, I'm actually going to have groups of this exponential happening, and it's just going to explode quickly. But we could look at it more simply as saying, what do we do if we keep this strategy up for 2 years or 3 years? Well, we're just going to be multiplying the top here by the amount necessary. We'll be growing the amount of months we have in the top. Okay. So now from everything we've learned, we should be able to kind of anchor it all into a little bit of a formula. And I've got it written out here, so let's maybe take our time to just really make some understanding of what's happening here. So from everything we have on the previous page, we can generalize the following formula for the future amount. A, based on an initial amount, initial investment P. So what do we have going on here? We have a future amount A that is based on an initial deposit P, where every single time that amount P is going to be at least kept the same and multiplied where the rate is divided by a certain number of years, or a certain number of instances where it compounds. There's a lot going on in there. So let's again bring it back to the story. In the story above, we were saying how every single time I was going to be growing it by 100%. Do we see that? So it's like right here, I've got 100 plus 100. So it's like I've got 1 plus 1 happening on the inside of the parentheses. And we can see that would make sense in that situation, because what is it that we were doing in that situation? We were trying to grow it by 100%. I was getting 100% return on my money. And how often was I getting 100% return on my money? Once a year. Versus in the other situations, what I was getting is I was getting 100% on my money twice a year, which is why on the inside of those parentheses, we started to see that it became a half. So how much were we getting? We were getting 100% rate of return for whatever I was putting in. I was getting the exact same amount out. But how often was that happening? That was happening 2 times. So we start to see the little bit of structure here where N is talking about the number of times I am getting this compounding, and rate is talking about the rate that the bank was originally promising me. Okay, well, what about out here? What are we looking at? This out here, N times T, is again going to be where I'm looking at N is the number of times that I compound each year. So as we saw above, in these situations, if I was looking at this is in instances of 12, then I would be having 12 of those instances happening. So I'm dividing the rate into chunks of 12, but the number of repeats that this is happening is also 12. So you can think of the top as being the number of repeats. And it's N times T because T is talking about how many years this is going on for. And I'll actually add that in. There's the number of times that you compound each year for T years. Okay. So inside of this is a story. The story being, I am taking an amount P, I am keeping it the same and growing it. I'm growing it in parts, in portions, right? My portion being the rate that I have divided by the number of times that I am repeating this process. And then up here, this is how long this has been going on for. It's been going on for so many iterations. Okay, but even if you make this more general, that idea of having an upper bound will still be happening. So let's talk about how even in this intuitive formula, we can still see that if I was going to run this thing with more and more instances where N keeps getting bigger and bigger, right, where the number, how frequently I repeat keeps getting bigger and bigger, that I can actually still pull out that upper bound E. And this requires a little bit of massaging. So let's start to build up the story. So to see this, we're first going to do some creativity, some change of perspective to make sure that everything looks like the example we had on the first page. We're going to try to make that E emerge. So first, let's start with exactly what would make sense to us, that the amount that we're going to have at the end is going to be dependent on how much we put in, and then this process of saying stay the same but grow by a fraction and repeating that so many times. So to find the hidden upper bound, the first thing we need to do is try to make it look like this structure that had an upper bound, make it look like this thing that eventually led us to our value of E. So how do we do that? Well, we need to be a little bit creative. The first thing that we're going to do is we're going to try to make the inside of the parentheses look just like the structure that we have in our table, which means that I need to have 1 plus 1 over something. And right now I have 1 plus R over N. So let's first make this where I have 1 plus 1 over something on the inside of the parentheses. That's simple enough. If we allow ourselves a change in perspective and creativity, we can look at this as 1 plus 1 divided by N divided by R to the NT. So if this feels weird, take a moment and look at the steps that I wrote just above that. All we're doing is kind of playing around with the idea that 1 divided by something is the reciprocal. So we flipped the fraction and put it on the denominator, changed everything's roles. What's the advantage of doing this? Well, now we have this 1 that appears on the top and looks very close to this 1 that we have right here. In fact, a lot of this looks similar. 1, 1 plus, 1 plus. We have something on the bottom. We need to make the top look like it matches. so that we can get it looking exactly like the structure. This part right here is still a little bit odd. Let's put it in blue. This part right here doesn't match this part right here, and we'd like it to. So let's do a little bit of massaging. We could make this into P times 1 plus 1 over n over r. And then up here, if we want to make n over r appear, why don't we just make that happen, right? We could absolutely put in n over r. Using the n that we have here, we'll just put it over r. We have to, of course, keep the same meaning, so we'll multiply by r as well, and then we still have that t. Okay, what was the advantage of doing everything here? Well, we can look at this entire thing and say, take a look. This bit right here is now the exact same thing as this bit right here. So if we start to make this where we run this entire thing faster and faster and faster, if we start to look at where the number of instances that I am playing with, where I'm doing this repeating, over a rate, which is going to be locked in by whatever situation I'm starting with. So if my bank sets a rate, then all I'm looking at trying to do is drive this n value up. Then the blue highlighting I have below here and up here are both going to be going up according to this table. Because after all, they're the exact same structure as what I had in the top. So what does that give us? That says that what I have is something that is 1, or P, times 1 plus 1 over, I don't know, something that is the same in the denominator and the top to the RT. And sure enough, that's enough for us to recognize that I could actually, if I was in the situation where I was trying to do this compounding continuously, I could replace all of this with E if I'm in a situation where I am doing this or looking for that upper bound. Oh, let's not make it that it goes to let's make it as an upper bound. All this has to be less than or equal to this is my upper bound. Okay. So from here, we see that exactly like we would thought, the upper bound of this growth language, is that we will always have to have an amount that is equal to P times e to the RT, or less than. So what I like to sometimes say is that it has to be less than or equal to P times e to the RT. So let's try putting together everything that we've found and see if we can summarize our thoughts in a couple of shortcuts for our future problems. Is it true that every exponential function of the form f of x equals b to the x is 1-to-1? Well, first let's make sure that we mark a little bit of the things that we mean by all this. B is just going to be equal to some number. So we can say b is equal to some kind of number, a constant. If b is a constant, and I'm just doing constant to the x power, that means that I'm doing more groups as we're going through this exponent. Is it true that this has to be 1-to-1? What does 1-to-1 mean? 1-to-1 means that for every question I ask into the function, I get one answer. No, that's not actually right, because functions always give me one answer when I ask a question. We're trying to figure out if the reverse also is true. If I have an answer, is it true that it must have come from one and only one question? Well, there's a few ways for us to think about this. The first way is we could always just go back to looking at our graph, and our graph looks like this for exponentials, where I'm always going to be intersecting down here at 0, 1. Right? Because if I put in 0 into this exponent, that's going to be a number to a 0th power. That's going to be an answer of 1. And then if we take one step over, it's going to go through, let's see, 1 comma b to the first, which would be 1 comma b, right? And then the second step would be 1 comma b to the second, etc., etc., etc. Does this pass the horizontal line test? Well, yeah, absolutely. We can look through this entire thing and say it passes the horizontal line test just nicely, wonderfully, good job. The other way we could think about it is we could think about it as saying, well, let's suppose that there were two different things, like b to the x equals the same thing, the same answer as b to another question. Let's call it b to the x1 question and b to the x2 question. Well, if this is the case, doesn't it make sense that if I have a number raised to a certain amount of repeating groups, and that same number raised to a amount of repeating groups, that those two amounts of repeating groups must be the same? So sure enough, whether you want to look at it as the horizontal line test or the logic, if you want to say that I have an answer, that answer must have come from one and only one question. Because if you think it came from two different questions, we can prove that those two questions are, nope, just one question. They're the exact same thing. It has to be. Okay, if an exponential function can be written in the form of b to the u equals b to the v, then, well, just as we discovered above, u has to be the exact same thing as v. So if we're talking about repeating 2 times 2 times 2 a certain number of times, is ever going to land on a number that is the exact same thing as another amount of repeated multiplication? Never at all. Otherwise, we'll have blown past our target or will not have reached it yet. Okay, so how can we use this when we're solving problems like we have below? Well, we can use it as a basis for interpreting our story. So let's take a look here where we say, use your findings above to solve the problem. So I'm looking at 8 is equal to 1 over 16 to the x. This is a difficult problem to solve if we try to do it directly, but if we want to use our logic instead, we might recognize that 8 and 16 are both numbers that 2 could grow up into. And so let's take a look. That would be 2 to the third is equal to 1 divided by 2 to the fourth. And then we have 2 to the x. Take a moment there, and if you need to, all I'm doing is recognizing that I have 2 to the third is 8, and then a double of that was 2 to the fourth, and I've got that all to the x power. Okay, well, what does that get us? Well, I could get the 2 to the fourth off of the denominator, try to get x alone. That would be if I multiplied both sides by 2 to the fourth, so it would be 2 to the third times 2 to the fourth is equal to 1 over x. Let's think. Oh, nope, that one didn't work. So from here, what can we do? I could make this look where it's 2 to the third equals 1 over 2 to the 4x, and let's try to remember why that is. Again, what we have is 2 to the fourth, so that means 2 multiplied by itself 4 times. That entire thing is being multiplied by itself x times, so it's like I have x groups of 4 groups of 2, so that means that I have 4x groups of 2. Okay, well, what can we do from here? 2 to the third equals 2 to the negative 4x. I could do that because it's really annoying me that I have an exponent on the bottom. But now doesn't this look like almost the same story? I've got 2 being raised to the third power and 2 being raised to the negative fourth x power, and I'm being told they're the exact same thing. So I can actually use my logic and say that that must mean that the 3 must be the exact same thing as my negative 4x. Because I'm looking for the amount of times I've repeated 2 around it. On one hand, I've got that I've repeated it 3 times, and on the other hand, I've got that it has to be the same as negative 4 times an unknown number. Well, that means that my unknown number has to be equal to 3 over negative 4. And we can go back and we can check this entire thing. If I put in to my calculator here, and I say, okay, let's go ahead and put it in the calculator. I'm looking for 16 to the power of 3 over negative 4, so let's put that in, to 3 divided by negative 4, made negative, there we go. That's going to get me, it looks like 0.125, which I know to be 1/8. You can check that in your calculator if you want. So on one hand, I've got 1/8 is the same thing as 16 to all of that stuff. So that means that 1 over 16 to everything there is going to be the same as doing 1 over what I have as an answer, and that's equal to 8, sure enough. Right there what we have. So this does actually end up working, this idea of saying we're going to just try to make the exponents, or the bases be the same so we can look at the exponents alone. What can we do for this next one? 1 over 27 to the x power. Whew, that's a lot to look at. I see a 3 on the other side. Maybe I want to look at it in terms of 3's. But 3 is to the fourth power and a lot of things. Well, okay, well, fourth power is really annoying. There's no reason why I need to have a fourth, or excuse me, the fourth root is really annoying. There's no reason I need to have a fourth root in there. I can always just look at a fourth root as being a 1/4 exponent. And I think that's going to be much better. So we'll do x minus 2 is going to stay there, but I'll put the fourth root into a 1/4 exponent. That looks much cleaner for me. On the left-hand side, that really looks like I have, what? 27 is 3 times 3 times 3, so it's 3 to the third. So I can write this as 1 over 3 to the third. And since I really want both sides to just be 3 to an exponent, I guess that's going to be my motivation for making this look like 3 to the negative third, and I'll get rid of the fact that it was on the denominator of that fraction. And sure enough, I have 3 to the 1/4 x minus 2. And then I can officially say that if the bases are the same, then the logic says that the number of times I'm repeating those groups must be the same. So I'll just jump into making those exponents have to be the same thing. That'd be 1/4 x minus 2, which I think from there we can just solve on out. So that'll be what? Negative 12 equals x minus 2, which means that negative 12 equals I guess we would add 2 to both sides, so negative 12 plus 2 equals x. So that would be, what, negative 10? There we have it. So we can actually solve for things within the exponents by just trying to set the bases the same and then looking at the amount of steps as being the thing I can actually set as equal. Okay. What about some of these things where I have like the number e? Well, e is again just a constant. Think of it like pi, if you will. It's a number that pops up from a process. Pi pops up from circles. E pops up from growth. It's the hidden language of growth. It's the number one common element, if you will. So what can we do in a situation like this? Again, we can just try to make it look like I have a common base. I have e to the 3x minus 1. And then on the right-hand side, I have e, it was to the square root, let's make it, or square root of e, let's make it 1/2 and we'll keep it on the denominator. But then we really quickly realize that if we don't want things on the denominator, we can just make the exponent negative. And on the right hand side, I'll have e to the 3x minus 1. That means that the 3x minus 1, the amount of groupings, the amount of repeated multiplications I've done has to be the same. And then I think from there, it's just simple algebra, right? 3x is equal to negative 1/2 plus 1 would be 1/2. And if I divide both sides by 3, that would be x is equal to 1/6. There you have it.